Okay, pre-cal, in this video, we are still in Unit 5, so we are still in the unit circle unit. So we are going to, in this video, talk about linear speed and angular speed. So the first thing I'm going to do is define these things for you. So the linear speed is actually the rate, as you would expect, an object moves along a circular path. Makes sense since we're talking about the unit circle. Okay, so if I've got a circle here, and let's say I've got this central angle at theta, and I want to know the speed at which an object would move along this path. So I am going to define this path right here. I'm going to define it as S, and that S, of course, is going to be the arc length So linear speed, we actually use, this is a, this symbol that I'm going to use is actually, it looks like a V, but it's actually just a Greek letter that represents linear speed, and it is equal to S over T. So this is our formula for linear speed. It just takes the arc length S and divides it by T, which in this case T would be the time to travel. Let's call it that. All right, so you're basically dividing the arc length by how long it is in time. All right, so that is your formula for linear speed. So now let's look at angular speed. Angular speed is a little different. Angular speed is actually the rate an object rotates about a fixed point. Okay, so again, we are going to use a Greek letter. All right, it looks kind of weird. It looks like a little wonky W. It's actually the lowercase omega. And its formula is actually theta, the central angle, divided by t. Okay, so this is the formula for angular speed. And remember that theta, of course, is going to represent the angle of rotation. And we're always going to measure this in radians. And so it is going to be the angle of rotation that the object moves in time. So t is still going to represent time here. All right, so using these two ideas, so these two formulas, we're going to look down here at example 3 because example 3 is going to illustrate both of these for us. So the first example, or the first part of the example here, during one delivery, the tires rotate at a rate of 140 revolutions per minute. All right, so we are finding the angular speed here. Find the angular speed of the tire in radians per minute. So, of course, in this circle over here, you've got 30. That's the diameter. And that means the radius would be 15. All right, so when we're looking at the rate here, if I'm looking for angular speed, I know I'm going to use this formula right here. So I'm going to need theta over t. So that is going to be time, of course. Well, one rotation, all right, so let's think about this. One rotation around the circle is 2 pi. Okay, so one rotation is 2 pi. We are used to that. We already know that from the unit circle. So that means if I'm told this bicycle is going at a rate of 140 revolutions, so 140 rotations per minute, that means that 140 times 2 pi tells me that it's actually going 280 pi radians, okay? So that's how we're going to measure that. So that's going to be my theta. So I'm going to put that right up here. Well, you technically don't need the radians yet. And then that's going to be over 1 because I am looking for the angular speed of the tire in radians per minute, so 1 minute. So that's just going to be 280 pi radians per minute. And you could also calculate this in your calculator, and it may be easier to think in terms of this. So that's how we would do that. Easy peasy lemon squeezy. All right, now we're going to look at part B. On part of the trip to the next delivery, the tire turns at a constant rate of 2.5 revolutions per second. Find the linear speed of the tire in miles per hour. Okay, now I want you to pay attention here. I'm giving you information in revolutions per second, but we want our answer in miles per minute. So we are going to have to do some conversion here. So I've got 2.5 revolutions, and those correspond, those revolutions correspond to an angle of rotation theta. So that is going to equal 2.5 times 2 pi because 1 revolution would be 2 pi. So that's going to give me 5 pi there. So now what I'm going to do is I am going to set up my equation. So I know my equation for linear speed is right up here. Okay, so linear speed is going to be this right here. So that gives me S over T. And please keep in mind that S, since it represents the arc length, I've got to use the formula R times theta in for S. So that's going to be R times theta over T. Well, I already found, or I already know that the radius is 15, and theta is going to be 5 pi. And then I know that that's 1 second. You don't really need the second, you just need the 1, but I'm just trying to illustrate something here. Okay, so this is going to be 75 pi inches per 1 second. All right, so that's what our answer is, but now I need to write it in terms of miles per hour. So what I need to do is I need to do a conversion. So I have 75 pi inches over 1 second, and I'm going to multiply that by 60 seconds over 1 minute. And then I am going to multiply that by 60 minutes in 1 hour. See, I've got to have it in terms of hours, so that's why I have to go from seconds to minutes to hours. And then I want it in miles. Well, right now I've got it in inches, so I'm going to need to go from inches to feet to miles. So I know that there's 1 foot in 12 inches. And then there's in 1 mile, there are 5,280 feet. Okay, so now it's just a matter of reducing my my amounts in seconds and inches, etc., etc. So watch what happens. The seconds go away, the minutes go away, the inches go away and the feet go away. So now I'm left with 1 hour and mile. So in the numerator, I have 75 pi times 60 miles over 12, 5,280. So 12 times 5,280, and of course this would be in hours. All right, and then I've just got to use my calculator, and I get approximately 13.4 miles per hour. I know it's lengthy, but it's not impossible.